Machine learning, often abbreviated as ML, stands as a pivotal branch within the broader field of artificial intelligence. Its fundamental purpose is to empower computer systems with the capacity to learn directly from data. This learning process occurs without the need for explicit, step-by-step programming for every possible scenario. Instead of being given rigid instructions, ML systems develop their own understanding and rules. They discern underlying structures and relationships within information. This allows them to adapt and perform tasks that were not specifically coded into their initial design. The core mechanism of machine learning revolves around sophisticated algorithms. These algorithms are designed to meticulously analyze vast quantities of data. Through this analysis, they are able to identify intricate patterns and correlations that might be imperceptible to human observation. Once these patterns are recognized, the algorithms leverage this acquired knowledge. They then use it to make informed predictions or intelligent decisions. This capability forms the bedrock of many advanced technological applications we encounter daily. A distinguishing feature of machine learning is its inherent ability to learn and continuously improve over time. As more data becomes available and is processed, the system refines its understanding. This iterative process leads to increasingly accurate and reliable outcomes. This approach fundamentally differs from traditional programming paradigms. In traditional programming, every rule and outcome must be explicitly defined by a human programmer. Machine learning, conversely, allows the system to discover these rules autonomously. The journey of a machine learning model begins with what is known as model training. This crucial phase involves feeding a specific algorithm a large collection of information. This collection is formally referred to as the training data. The training data serves as a comprehensive set of examples for the algorithm to learn from. It provides the necessary context and instances for the system to build its internal representation of the problem it aims to solve. The quality and quantity of this data are paramount. During training, the algorithm undertakes a continuous process of adjustment. It systematically modifies its internal parameters and weights. These adjustments are critical for optimizing its performance and learning capabilities. The primary goal of these adjustments is to minimize errors in its predictions or classifications. The algorithm iteratively compares its outputs with the correct answers provided in the training data. It then fine-tunes itself to reduce discrepancies. This iterative refinement improves the algorithm's ability to accurately predict outcomes for future data. It also enhances its proficiency in classifying different types of information. The model essentially learns from its mistakes, becoming more precise with each iteration. Once the training phase is complete and the model has achieved a satisfactory level of performance, it transitions to the prediction phase. At this point, the trained model is ready for practical application. It is deployed to perform its intended function. In this phase, the model is presented with new, previously unseen data. This fresh input is commonly known as test data. The model then applies the knowledge it gained during training to make predictions or decisions on this new information. Machine learning encompasses several distinct paradigms, each suited for different types of problems and data. One of the most prevalent is supervised learning. This method learns from data that has been meticulously labeled. In supervised learning, each piece of input data is paired with its corresponding correct output. The algorithm is essentially taught by example, with the desired outcome explicitly provided. This direct feedback guides its learning process. Applications of supervised learning are widespread and impactful. They include image classification, where models learn to identify objects within pictures, and predicting house prices based on various features. These systems excel at mapping inputs to known outputs. Another significant type is unsupervised learning. Unlike its supervised counterpart, this method learns from unlabeled data. The algorithm is given raw information without any predefined correct answers or categories. The objective of unsupervised learning is to discover hidden patterns, structures, or relationships within the data itself. It seeks to organize and make sense of information without explicit guidance. This approach is particularly useful for exploratory data analysis. Common applications include customer segmentation, where businesses group customers based on purchasing behavior, and anomaly detection, identifying unusual data points that might indicate fraud or system errors. It reveals insights that might otherwise remain obscured. Finally, reinforcement learning represents a dynamic approach where an agent learns through interaction with an environment. It operates on a system of trial and error, much like how humans learn new skills. There is no explicit training data. The agent receives rewards for taking correct actions that lead to desired outcomes. Conversely, it incurs penalties for incorrect actions. This feedback mechanism encourages the agent to optimize its behavior over time to maximize cumulative rewards. Reinforcement learning has found remarkable success in complex domains. These include game playing, where AI agents learn to master intricate strategies, and robotics, enabling robots to learn how to perform tasks in dynamic physical environments. The transformative power of machine learning is evident across an astonishing array of industries and daily life. In healthcare, ML is revolutionizing diagnostics and treatment. It assists in the early detection and diagnosis of diseases by analyzing medical images and patient data. Furthermore, ML accelerates drug discovery by predicting molecular interactions and optimizing compound selection. It also enables personalized treatment plans, tailoring therapies to individual patient profiles for improved efficacy. The finance sector heavily relies on machine learning for critical operations. Fraud detection systems use ML to identify suspicious transactions in real time, protecting consumers and institutions. Algorithmic trading leverages ML to execute trades at optimal times based on market predictions. ML also plays a vital role in credit risk assessment, evaluating loan applications with greater accuracy and fairness. These applications enhance security and efficiency within the financial landscape. E-commerce platforms are deeply integrated with machine learning to enhance the customer experience and drive sales. Recommendation systems, powered by ML, suggest products or content based on user preferences and past behavior. Targeted advertising utilizes ML to deliver highly relevant ads to specific consumer segments, increasing engagement. Customer service chatbots, often driven by ML-powered natural language processing, provide instant support and resolve queries efficiently. Beyond these core sectors, machine learning extends its influence to numerous other domains. Self-driving cars are a prime example, where ML algorithms process sensor data to navigate, perceive surroundings, and make driving decisions autonomously. Natural language processing, or NLP, a subfield of AI heavily reliant on ML, enables computers to understand, interpret, and generate human language. This powers voice assistance and translation services. Predictive maintenance in manufacturing uses ML to forecast equipment failures, minimizing downtime and optimizing operations. The successful implementation and deployment of machine learning models hinge on several critical factors. Foremost among these is the availability of large datasets. ML algorithms thrive on vast amounts of information to identify robust patterns and generalize effectively. Equally important is the availability of high-quality datasets. Data must be clean, accurate, and representative to prevent biases and ensure reliable learning. Poor data quality can severely undermine a model's performance and utility. Powerful computing resources are also indispensable. Training complex ML models, especially deep learning networks, requires significant computational power. High-performance processors and specialized hardware like GPUs are essential for efficient model development. Finally, the continuous development of sophisticated algorithms is a key driver of ML success. Advances in algorithmic design enable models to tackle more intricate problems and achieve higher levels of accuracy and efficiency. The field of machine learning is in a state of constant evolution. Researchers and practitioners are continuously developing new algorithms, techniques, and architectures. These innovations push the boundaries of what ML can achieve. As the volume of data generated globally continues to grow exponentially, machine learning is poised to play an increasingly significant role. Its ability to extract value and insights from this deluge of information will become even more critical. Machine learning is expected to transform industries across the board, from healthcare and finance to transportation and entertainment. It will drive innovation, create new efficiencies, and fundamentally improve lives in countless ways, shaping the future of technology and society.